So yes, I am sort of divided between University of Southampton and University of Iceland right now. And this work is done in the group of Professor Pavlos Lagoudakis, which is an experimentalist group focused on exciton-polariton physics. And their labs are divided between Skolkovo Institute of Science and Technology. So let me just, can I ask, do you see my cursor on the slides?
Yes.
Okay, perfect, thank you. So yeah, Professor Lagoudakis' experimental group has labs both in Skoltech and University of Southampton, but I'm mostly working at University of Southampton and a little bit in Iceland too. So the title of my talk is Programmable Networks of Exciton-Polariton Condensates. And first, before I dive into the physics, I would like to, well, remind everyone where Southampton is located. This may be a little bit silly because this is a UK webinar, so everybody should know where it is. But we have a really excellent lab in Southampton at the University and School of Physics and Astronomy. But what's even more important is that we also have a very fantastic coffee machine. So if you ever come to visit in Southampton, then please knock on our door. We'll be happy to serve you a cup of coffee and discuss some physics. So anytime you're in the neighborhood. But the group is really quite large. We're about 20 researchers spread across, well, me in Iceland and everyone else between UK and the Moscow region in Russia, where they have recently constructed this new university, which is for short called Skoltech, but its larger name is Skolkovo Institute of Science and Technology. And we really focus on collaborative research effort. We work with University of Cambridge, Sheffield, University of Warsaw, Würzburg. So we really work with a lot of excellent groups focused on polariton physics. Now, so I'm going to outline my talk on this little funny map of my country. So this is a very old map of Iceland drawn in 1590 by Guðbrand Þorláksson. And for the first leg of this talk, I'm going to discuss the strong light matter coupling and the systems where this phenomena occurs. And so you can see in this little animation that it is a photon which is trapped between two mirrors, which excites an electron. And if the coherent exchange of energy is fast enough, then you end up with new hybrid states that are called exciton-polaritons. And I will go into more detail about that later. Then we're going to continue our journey, and I'm going to discuss the Polaritan Condensate and how this occurs at much higher temperatures than usual ultra-cold atom experiments. And then I am going to go and discuss the coupling mechanism between two interacting condensates, which forms the basic building block of all of the extended systems that we create in our microcavity samples. And scaling up, I will show lattices with more than 100 coherently coupled and interacting condensates, all exchanging information. And I will go into a little bit more exotic geometries, polygons, which display a hallmark of superfluids or quantum fluids, vorticity. And then if I have time, I will try to discuss a little bit about applications and technologies that could potentially benefit from polariton physics, such as analog simulators, neuromorphic computing devices, logic gates, and so on and so forth. Now, the first part of the talk, strong light matter coupling. So we're going from Reykjavik towards a town called Vík, where there is a volcano, which many people may be familiar with. So this is Eyjafjallajökull, very easy to pronounce, no problem there. And what I want to do to start with is to introduce the system in question that we're working with. So the system is a semiconductor heterostructure. It's a planar microcavity. Of course, many different types of cavities and microcavities, but we are going to be exclusively focused on the planar versions. So this, sorry, my phone was ringing. So this type of a microcavity is embedded with quantum wells. In our case, we'll be focused on inorganic quantum wells of indium gallium arsenide type. which hosts Vannier-Mott exciton modes. And these exciton modes can couple with photonic mode, which is confined in this structure. So how the photons are confined is that if you look at the top schematic, you are constructing distributed Bragg reflectors, which are very high quality mirrors. So we can reach quality factors in the tens of thousands. And so you can really confine photons for a long time to interact with excitons in these quantum wells and achieve strong light-matter coupling. And so the typical time scales and energy scales we're working with here is in the milli-electron volts, picoseconds, and the temperature we need to work with, because milli-electron volts is quite a low energy, binding energy for the excitons. So we need to work at cryogenic temperatures, so 6 Kelvin, 5 Kelvin. So liquid helium experiments. Now, strong light-matter coupling has been realized since the 90s, where these two gentlemen observed for the first time anti-crossing behavior or normal mode splitting in semiconductor microcavities, which was direct evidence of strong light-matter coupling. So this has been known for quite a long time that you can achieve strong light-matter coupling in these high-quality microcavities. And so what is going on in these cavities? What does this data mean? Well, what is happening is that, like I said previously, that you have a photon mode, which you can find between your DPRs, your distributed Bragg reflectors. And this photon mode interacts with an excitonic mode inside the quantum well. So it can excite an electron to populate the 1s exciton state inside these quantum wells. And the reduced dimensionality of these structures means that it can couple very efficient to this exciton through its dipole oscillator strength. And sort of the most intuitive way to show what is happening is just to plot the photon branch. So this is a single photon mode, which is inside the cavity. So this orange one that I've schematically shown here. And it has some in-plane momenta, which approximately is parabolic, but this dispersion relation is a little bit more complex than that, but approximately parabolic. Now, the exciton, which I've plotted here in blue, is much, much heavier in mass and therefore appears almost flat as a function of in-plane momenta of the microcavity. So in-plane momenta means that it is the momentum in the transverse plane of this structure. And what happens is that when you have energy exchange between the exciton and the photon modes, and you write your typical Jaynes-Cummings Hamiltonian, you get new eigenmodes of the system, which are the upper polaritons and lower polaritons. And these modes are hybrid quasiparticles, or just quasiparticles, but they are hybrid because they contain a bit of the photonic component and a bit of the excitonic component. So they can inherit both the bad and the good properties of excitons and photons. And we will see that the good properties, they really outweigh the bad properties of these particles. So we can do a lot of new physics with these Polaritan modes. And here is just some experimental data showing how it looks like in reality. So if you do a typical reflectivity measurement, if you do not have a quantum well with excitons inside your cavity, then you only have a single dip, which is the photonic resonance of your cavity. But if you add excitons and they couple with the photons, then you get your normal mode splitting, and suddenly you have two peaks or two dips in your reflectivity spectra. And this is how it looks like if you extract the photoluminescence by just putting a camera and looking at either the reflected light or transmitted light through a cavity. You can resolve in energy and momentum the light that's coming out of the cavity to resolve the dispersion. And notice that the upper polariton is much weaker in intensity than the lower polariton, because polaritons are quite interactive and can thermalize. So they are much more keen to populate the low energy states, which actually plays a little bit into the phenomenon of condensation I'll talk about later. So it is good to mention what I mean by strong coupling in comparison to what we're more familiar with is weak coupling. So weak coupling is the typical population inversion effect where you have standard lasers working with stimulated emission of photons. But as you increase the coupling strength, which is quantified so-called vacuum Rabi oscillations, and if this coupling strength G is larger than the typical line widths of your particles in your system, so if it's larger than the line width of the exciton or photon, then you can start resolving this normal mode splitting and can see the new modes in the system appearing, which are the Polaritan modes. So this is really basically the difference between, or what sort of defines strong coupling in comparison to weak coupling. And then there is ultra strong coupling and deep strong coupling, but I will not go into that. That's a little bit beyond what I work on. So these are the Polaritan modes that we're working with in these semiconductor structures. And maybe I should have mentioned that they are bosonic, which is going to play a big role in the next part of my talk, which is the Polaritan Condensate. So in 2006, there is the first demonstration of Polaritan Bose-Einstein condensation, although it's a little bit debated in our field whether it's proper to call it a Bose-Einstein condensate, because how they realize these condensates of polaritons is not by cooling the system. This is not done, but rather it is by ramping up the laser power, which excites a lot of particles in our system and leads to this condensate phenomena. So it's a non-equilibrium system, and therefore it doesn't have the proper equilibrium characteristics, which conventional Bose-Einstein condensates have. But nevertheless, there have been loads of experiments showing this phenomenon of condensation of polaritons in many different materials and reaching room temperature using organic materials, perovskite materials, transition metal dichalconides, and so on and so forth. So there's a lot of different systems that can give access to this condensate. And what is happening physically is that if you bring a laser to your sample at normal incidence and you tune it to be off resonant, so you tune it to be very high in excitation energy, you will create a lot of free electron and hole charge carriers. And because they are quite interactive, they will very quickly relax through phonon scattering to form a hot reservoir of excitons. So this is the excitonic state here denoted by these red particles. But then if you increase the power of your laser more and more, and you increase the density of the excitons in the reservoir, then at some critical power, you will achieve, you will approach the quantum degeneracy limits, and there will be a bosonic stimulated scattering event, which means that as soon as the ground state starts getting populated, the population will shoot up and the scattering will be enhanced until the system clamps and saturates. So it is something very similar to a laser, but it also has a lot of similarities to normal atomic condensates. So we are sort of in between these two systems, the laser and the atomic condensates, especially because this is a power-driven phenomena. So you need the laser to drive the system, and as soon as you remove the laser, you have no longer any condensate. And you can see this here in this experimental data from the seminal Kasprak paper, where as a function of power, so you can see here they are 0.5 below threshold, at threshold, and 14% above threshold. And you can see that in momentum space, in Fourier space, there is a sudden huge amplification in the ground states, and the line width narrows dramatically, which is an indicator of condensation. Now, a very important part of my talk is going to be about optically engineering these condensates. So there is one mechanism that we can rely on to engineer optical potentials for these Polaritan condensates using the non-resonant lasers that we use to stimulate them. And how this works is that when you excite the sample with your laser, you're not only creating a condensate, but you're also creating these, this excitonic reservoir, which I denoted here with these red particles. And they are still happy there in the background. They don't go away. And any Polaritan waves that are in the system, they are also partly excitonic. And excitons interact repulsively. They bounce off each other. So you can tailor this reservoir of excitons. You can pump locally, you can spatially modulate your laser light to create a complex potential landscape in the plane of your cavity. So how it looks like is that if the focused light on your cavity is this denoted with an E, the potential which polaritons feel in the cavity plane is going to be directly proportional to the intensity of the focused light with two coefficients. One is purely real, which denotes the repulsive character of this potential, and the other is purely imaginary, which denotes the stimulated scattering or the optical gain that the condensate experiences. And how it looks like is that when you pump locally, you create a lot of polaritons at the position of your pump spot. So this red region here that you see my cursor moving over is a condensate of polaritons. But because you have put them in a very non-equilibrium setup, you put them on top of a potential hill, they will naturally ballistically diffuse away from this hill. And you can see here on the left side of this potential hill that you have induced with your laser, polaritons have leaked away and are forming now standing waves between the edge of your system and the pump spot. So you have artificially created something like optical confinement of the polariton modes. And in the other direction, they just ballistically flow away quite freely. So this is a very neat thing, because this means that we can create not just a condensate with the laser, but we can also put it in a condition where it senses a localized potential landscape, complex one for that matter. And we can do this by, we can exploit this by creating multiple pump spots. So this is very easy. You can easily modulate your laser to create multiple pump spots, and you can get your then condensates to interact over very, very long distances. I will go into this in a bit more detail later. So here we see a schematic image of the laser-induced potential, which is roughly Gaussian-like, because the laser light is Gaussian in profile. And here we have experimental images showing the intensity or the density of the two condensates, which have coherently phase-locked and synchronized to form these very nice interference fringes between themselves. So there is this strong ballistic flow with high K vector of polaritons flowing from one condensate to another. Okay, so before I continue discussing the coupling mechanism between two condensates, I'm going to describe a little bit more how the single condensate looks like. So let's say that you focus with a very narrow laser, with a very tightly focused laser on your cavity sample. So full width, half maximum, we go almost to the limit of our optical setup. So we cannot really go smaller than 2 or 1 microns in full width, half maximum. And how the condensate looks like is that it is this very bright, intense spot in real space. This is the near field image. And in K space, in momentum space, which is the far field image, we see a bright circle. And this is very counterintuitive, because how can we talk about condensate when it is obviously not populating the low momentum modes? Well, that is because this isn't really a proper condensate, but it's rather a out of equilibrium condensate. So you locally drive it to condense at the position of the laser, but then there's a lot of particles that move out of the spot, which are still coherent. And this is the signature of these particles that have moved away from the spot, which gain this wave vector Kc. So this is like a ballistic fluid, like a little antenna that is sending polariton waves radially in all directions. And so if this is a ballistic fluid, then it means it has a very rapidly evolving phase profile. So we can do interferometry and we can extract the phase profile of this condensate, and we can see that it has this very rapidly evolving phase because it has such a high momentum. It's populating such a high momentum component. So this is a very unique type of quantum fluids that occupies these high momentum components, and it leads to a lot of interesting physics, which hopefully I can talk about if I have enough time. Okay, now a little bit about how we describe these systems theoretically. So very briefly put, we write a complex generalized version of a Gross-Pedievsky equation. So a Gross-Pedievsky equation is the standard mean field model to describe quantum fluids. But we are going a little bit more towards the direction of a Ginzburg-Landau equation, which can have complex coefficients. And so this is a strongly non-Hermitian model, which needs to be non-Hermitian because you have losses of polaritons. So polaritons are very lossy. They have a lifetime of about 5 picoseconds, which is captured with this gamma parameter. And then they have some optical gain. There's gain coming into the system because there's an exciton reservoir, which is described by this rate equation, which stimulates and populates. It amplifies all the polariton waves in our system. And then you have your typical Polaritan-polariton nonlinearity, which is quite standard in Gross-Pedievsky formulas. So this is just to give you a rough idea how we describe the system in a mean field approach. All right, so now we're going to talk about how two of these condensates interact with each other, and this is quite a nice piece of physics that we recently developed. When you do the measurements with two pump spots and you play around with quite a fundamental parameter defining the coupling between the two condensates. So these two bright spots, these are the condensate densities that are being pumped by two lasers. And we're going to change the separation distance between the two condensates. And what we see in the photoluminescence, so this is the light that is coming from the cavity. This is the light coming from the polaritons, which leak out of the cavity, and we can capture them just using a normal CCD camera. And we see that when we change the distance, the number of interference fringes between the two condensates is evolving. It's changing. One by one, there is new and new and new interference fringe appearing. So there is apparently some sort of a synchronization condition that is being satisfied. And there is a specific standing wave mode between the two condensates, which is more favorable, which is more robust than other modes in the system. And we can see it both in the real space and K space, but also it's quite pronounced in energy resolved K space, where you see these modes appearing in a step-like fashion. Well, maybe not step-like fashion, but they sort of fade in and fade out gradually as you change the distance in the system. And what is quite interesting is that there are specific distances where your condensate diode, or these two condensates that are interacting with each other, they don't just populate a single well-defined energy, meaning it's a stationary state, but there are distances where they occupy two energies at the same time. So these are the gray regions here in the integrated spectral weight, which is given by these blue and red lines. So the red line is red line is even parity modes, and the blue line is odd parity mode. So parity is basically, is it an even or odd number of interference fringes between the condensates? So what does this mean? It means that this out of equilibrium driven system, it can stably populate in the quantum fluids two energies at the same time. It doesn't relax to just a single energy, but it can be driven into a bichromatic state, a non-stationary state. And so it typically would look like something like this in the energy resolved K space. So you see two spectral features corresponding to an even and odd parity modes. And if we do a quick simulation using exactly the Gross-Pedievsky treatment, how it would look like in real space is that there is something like a Josephson or a Rabi-like oscillation of the particle density between each of the condensate spots. So you can see it here, this oscillation, which is happening at gigahertz frequencies. And we can verify all of this by doing, again, interferometry. One of the good benefits of working with Polaritan condensates is that all of the information of the condensate is encoded in the emitted cavity light. So once you excite a polariton and it decays, it emits a photon that contains all the information about the condensate. So you can do all your standard optics and interferometry and homotime methods to capture information about the density, the phase, the spin and polarization and of the condensate, and do everything time resolved and energy resolved. So this is a really unique advantage of working with polaritons. And doing the interferometry in this experiment, we were able to verify through looking at the visibility of the interfered light between the condensates that there are robust oscillations in the first order correlation function, which means that this is a coherent superposition of two modes. And we published this work in communication physics, which we called time delay polaritonics. And why it's called time delay polaritonics, I will get to that in a second. And this is the person who really led this experimental effort, Dr. Julian Tupfer, who's now moved on towards greener pastures, working at some company in Germany, I believe. So why did I say time delay polaritonics? Well, the reason is because the signatures, the spectral signatures that we're seeing from our two coupled condensates, they are showing something that's very similar to the time delay dynamics in many other systems. So even just coupled candle flames, electronic circuits, neuronal systems, other biological systems, or just coupled semiconductor lasers, they're all time delay physics, and they show precisely the same kind of phase flip-flop behavior, going from an even to an odd parity mode, or an in-phase anti-phase parity mode. So we did a little bit more thinking, and we realized that this type of quantum fluid that we have developed, it then has a lot of like connection with many things in the real world. So time delay is a very ubiquitous phenomenon. It appears in pandemics like the COVID pandemic. It's in your commute when you're on your way to work. There is time delay effects, economics, communication, and something quite funny, something that we experience probably all when we're trying to tune the shower temperature in the morning, because there's a little bit of delay when you try to change the temperature of water. So time delay is really everywhere in nature. And so we figured out that because this is a ballistic Polaritan condensate, not the conventional cold atom condensate, the ballistic nature of the system means that it leads to momentum components or Polariton modes that need to travel some finite distance from one condensate to another. And this distance is macroscopic. It's huge. You can see it here on this image that it's much larger than the peak-to-peak distance of the interference fringes, which denotes the wavelength of the system. And it's much larger than the full width half maximum of the condensates. And when you have such a large distance, then it naturally begs that there's going to be delay in the interaction between the two condensates. And we wrote up a model, we derived a model, which was very similar to the famous Lancaster equation. So this is an equation that comes from semiconductor lasers, but it had the nonlinearities of polaritons, but it had now this coupling term, which is something like a Josephson coupling term, but with a time delay factor now, given tau. And so just to emphasize, this kind of a coupling is very, very different from usual bosonic Josephson junctions, where you have evanescent coupling between condensates. So here we have ballistic time-delayed coupling, but in conventional quantum fluids, you usually have evanescent tunneling or Josephson coupling between quantum fluids. So this is the major difference between the Polaritan fluids and other quantum fluids, which I want to emphasize. And of course, it brings in a lot of questions about sort of stability theory, chaos, limit cycles, self-sustained oscillations, and a lot of interesting nonlinear dynamics that we're currently investigating. Okay, so I hope I've convinced you that there is a new type of physics in how these Polaritan condensates interact. And now I want to talk a little bit about how we scale up the system. So we're going to go towards lattices. So Polaritan systems, conventionally, when you want to do lattices to simulate some Hamiltonians, you have to irreversibly engineer your microcavity sample to confine the photonic mode in such a way that it mimics some lattice Hamiltonian. So I hope you can see here that there is some structured patterned microcavity surface that has these kind of barrel or pillars that are connected with each other. So this is a lithographically etched microcavity that is essentially just a photonic crystal. It's a photonic crystal that gives rise to these Polariton hopping between lattice sites. And you can use this to create all kinds of lattices, like the Honeycomb Lattice, square, leap lattice, triangular lattice, so on and so forth. And you can use it to do all kinds of neat physics, for example, topological physics, because we know that lattices can be enhanced with topological properties. under the condition that you break certain symmetries. Okay, but we don't want to do this. We want to use our lasers because we like working with lasers. They're very nice because, well, first of all, if you don't like the pattern that you create on your microcavity sample, you can just reprogram your laser using a spatial light modulator, and you can create a new pattern. So everything is completely reversible if you just use laser light to create the condensates and the corresponding potential landscape. So how it looks like, here is an animation showing 9 condensates that we are in situ tuning using holograms that are created with a spatial light modulator. So this is just a piece of technology that's been known for a long time, and it allows us to create huge networks of Polaritan condensates in various graph topologies and geometries. So we want to use this instead of the lithographically etched cavities. So everything here is going to be done all optically. So here's another animation of a square lattice that shows the Polaritan condensates all synchronized in some nice block mode. And later on in this animation, we morph it into a triangular lattice. Again, you notice how the interference pattern is changing between the condensates, meaning that they are occupying different block modes as you change the lattice constant in the geometry. Next up is going to be the Honeycomb Lattice. It looks like this. So this just emphasizes that we have a lot of lattice structures that are accessible using just spatial light modulators. And doing some straightforward block calculations, we can create all kinds of fancy lattice dispersion block modes with band gaps and extreme points like Dirac cones or flat bands. And we published very recently a paper in Nature Communications, which was driven by Dr. Lucy Pickup, my colleague in Southampton, where we showed that we could synthesize a non-Hermitian version of the famous Schrieffer-Heger model, which is one of the simplest topological models that you can create. And how we did this is that we created these chains of condensate with only patterned lasers. So we could, when we turned off the laser, we could change the shape to add more condensates, create defect states, and do all kinds of interesting reversible physics with our system. And I mentioned defect states. So this is one neat thing that we can do by just removing one pump spot in the laser pattern, or changing, creating a localized defect by changing the lattice constant a little bit between 2 pump spots, whereas everything else is more homogeneous. And indeed, we can create these normal crystal block condensates, which are given here by this line profile, red line profile here. And then we can see clear defect condensation, which is something like a gap solid that we can induce by doing these kind of defected patterns. And another thing that we can do with these spatial light modulators is that we can overcome a lot of inherent disorder and inhomogeneities in the sample. So if we just focus a lot of laser spots and create a lot of condensates on the surface of the microcavity, then we get something like this picture here in panel D. And this doesn't look very nice. It's a little bit messy, right? But if we create a very simple feedback mechanism, an algorithm that extracts the photoluminescence of each spot and feeds it into an algorithm that tries to balance the photoluminescence or the density of each spot, then we can achieve a much nicer and a homogeneous system of condensate. So this is something much, much nicer. And this is kind of using the power of spatial light modulators to overcome any disorder in your landscape, which is quite a powerful technique, because it means that you can create these huge networks of condensates with a much better coherence length and synchronicity in the system. So in these right panels, I show here on a color scale that goes from blue to sort of pinkish brownish. This is the G1, or the first order correlation function. In optics, people use mu instead of G for the first order correlation function. But basically, we see that going from panel F to G, using the feedback algorithm, we have massively increased the coherence in the system. So everything has become much more coherent, and this is a truly macroscopic quantum fluid that is interacting across this lattice. And this was published recently in Optica, and this was led by Dr. Julian Tupfer. And I really love this image that was also on the front slide of my presentation. This is measured density coming from the Polaritan condensates. This is their measured density. But when I looked at it first, I thought this looks almost one-to-one to a simulation. It looks really, really just nice with all these perfectly symmetric interference fringes. So we really developed new techniques to make these macroscopic fluids more coherent. Okay, and other things that we can do. So these quantum fluids, we can go from two different regimes. So far, where we have focused our laser light, we have created a condensate, which is denoted with these panels A and D. So if you focus your laser light with these pump spots here, which are the bright Gaussian profiles on this black map here, correspondingly, they create excitons that create these kind of potential hills. And then you get your condensates, which is schematically given by this red envelope here. And this is what I've been showing you so far in my talk. This is kind of these ballistic condensates that we've been working with. But we can also go into a different regime where we can optically trap the condensates. So here they are ballistic and gain guided. But if we squeeze the distance between the pump spots, if we contract and reduce the distance between the pump spots, at some point there is a transition where the condensate no longer appears at the top of the pump spots and is ballistic. It instead collects in the potential minima between the pump spots, and it starts mimicking the more conventional condensates that we know from cold atoms in optical lattices. So this is something like a non-Hermitian complex version of cold atoms in optical lattices. And we demonstrated this quite recently by doing a very simple experiment. We created a lattice, a leap lattice specifically, and step by step, we reduced the lattice constant between the pump spots. And we could see in the photoluminescence that for large separation between the pump spots, we had this ballistic condensates interacting and synchronizing. And then as you decrease the lattice constant more and more, you started seeing some very crazy and funky patterns in the lattice. So there was some sort of a mode competition going on in our system where you are competing over where trapped condensate is competing with a non-trapped condensate. But eventually the trapped condensate wins when you reduce the lattice constant enough. And here in panel E, you see sort of Gaussian-like condensates collecting in the potential minima of this pumped lattice. So this is the limit of proper evanescently coupled bosonic fluids, whereas in the other limits, panel A is the ballistic version. So this is just a demonstration that we can continuously tune from one limit to the other. And this was published recently in Nature Communications, and this was pushed by Dr. Sergei Alyatskin at Skoltech. So really nice piece of work coming from him. Now, let me see. I think I have just enough time to talk about this last part, but I will probably skip about the applications because I don't think I have time for that. So the next part of the talk, where we go to the Westfjords, where you can find a lot of cute puffins, I want to talk about polygons of vortices, which can lead to macroscopic quantum vorticity. So since this is a quantum fluid webinar, I think everybody's pretty familiar with the phenomena of quantum vorticity. So when you have an order parameter or a wave function, it implies that there is irrotationality in it, which means that the velocity field of your particles is defined by the gradient of the phase profile of your wave function, which means that you can have these localized topological defects where the phase circulates or winds in integers of 2 pi. So this is like, this is basically just quantized circularity or vorticity. And this has been observed before in Polaritan condensates, just as in almost any other types of superfluids and other types of condensates. And this is a big ongoing investigation in polaritons to sort of optically manipulate this quantized vorticity in Polaritan fluids. And it is worth mentioning that we are sort of at the boundary from proper quantum hydrodynamic vorticity and just optical vorticity. So we know from the development of nanophotonics, metamaterials, and all kinds of new lacing devices, optical vortices have become increasingly more popular as elements for information processing, storage, or communication. So this is just a brief sort of two recent review papers about optical vortices. And since polaritons are so optical, it is basically a fair game to say that they have a lot of similarities with optical vortices. Now, but what are we going to do? We are actually going to exploit a well-known phenomenon, which is geometric frustration. So we are going to invoke a concept from spin systems. So we know that in spin systems, there is something that's called ferromagnetic and anti-ferromagnetic couplings. And if you arrange spins, such as Ising spins, in a triangular geometry, you can end up with a frustrated state when there is an anti-ferromagnetic coupling between the spins, because there is no unique way for the ground state to be defined, because the third vertex in this triangle, it has the same energy whether it's going to be a spin up or spin down. So there is this geometric frustration in the system, which is eliminated if you make it a square instead of a triangle. So any odd-numbered polygon will be frustrated if you have anti-ferromagnetic couplings between spins. But if you relax the constraint on the spins and you allow them to rotate freely on a plane, you actually have XY spins, which are planar rotors that were which are an integral part of the Brzezinski-Kusterlitz BKT theory. And there you lose your geometric frustration, because now again you obtain a unique ground state, which is these rotating spins along the triangle. And these rotating spins, they're basically a little bit like a vortex, because you can let the spins rotate clockwise or anti-clockwise. And so we started thinking, can we do something like this with the condensates? Because if we think about it, each condensate has something like an XY spin because it has a phasor. There is a phase degree of freedom, which is just a unit vector on the unit circle in the complex plane. So if we say that each condensate is something like an artificial spin, an XY spin, then maybe we can induce vorticity by creating a geometrically frustrated polygon of condensates. So here are some experimental images that show what I mean by associating a spin to the face of the condensates. So here are two condensates that form a bound state, which is, anti-bound state, or an anti-phase state. And in this case, the two spins would be opposite. So the relative phase the relative phase difference is pi. But then if you change the distance, you get an in-phase condensate coupling, which is like a ferromagnetic coupling. And now the spins align parallel. Again, I spins in quotation marks. There aren't any actual spins in the system. We're just looking at the phase. And so on and so forth. So you can do this. And this plays into the results that I was showing at the start of my talk. And so we did the experiment and we started creating these massive polygons. And we could see very clearly that if we created even numbered polygons, so here we have a hexagon, an octagon. Let me see. This is an octagon. And I think this is, again, this is a heptagon, 10 vertices right here. Yeah. And we could find the states that show this antiferromagnetic and ferromagnetic arrangement of the spins. And all of this could be tuned by just playing with the size of the polygons, because the size of the polygons determines how efficiently the condensates couple and whether it's going to be ferromagnetic or antiferromagnetic in nature. And here's a little animation that shows, again, the power of using spatial light modulators. So we can really continuously, gradually tune the size of these polygons. and extract all of these beautiful interference fringes coming from the coherent interaction of these condensates. And I like this image, this animation a lot because it's a little bit spacey. And so first thing I thought when I saw this animation was, of course, this group of guys probably would have appreciated too, maybe even had it in one of their music videos. And then we continued. So on this slide, on this previous slide here, I was showing you even numbered polygons, but we need to do an odd numbered polygon. And indeed, if we do the experiment, we create a pentagon, an odd numbered polygon, we can see that there is going to be quantized vorticity in the system. So we did, again, interferometry, extracted the phase difference between each condensate, looked at the phase in the center of the system, and we could see that there was a rotating phase flow. So every condensate has a phase slip of 2 pi over 5, which if you walk the circle of if you walk along the pentagon, 2 pi over 5, 2 pi over 5, so on, so forth, it gives you full 2 pi rotation. So this was a verification that indeed we could, by just exciting odd numbered systems, we could get vorticity in our system. And we could even go beyond that. We could create vortices with a vortex charge of 2, which means angular momentum of value 2. And this is very unique because vortices of high angular momenta are usually quite unstable. Thermodynamically, they're quite unstable. But because this is an out of equilibrium quantum fluid, we could manage to stabilize them. And so let me see what is my time. So I am going to now go very fast over these results. Sorry. Here's a little bit of analysis about angular block modes, which describe the physics of the system. I'm going to skip this. Sorry about that. Just a brief word on this slide. So doing again interferometry, extracting the correlations between different condensates and comparing against theory, we were able to verify that we could create vortices of charge 1, 2, 3. And so this is a system that gives you access to all kinds of values of the vortex charge, which is quite uncommon for quantum fluids. And so that's the take-home message. And I'm going to skip this last part because I have run out of time. Very sorry about that. And I'm just going to go here to the last slide. Excuse me. I swear this was on time in my head. But anyway, I'm going to stop now, and I'm ready for your questions. Thank you very much.
All right, yeah, thanks a lot, Helgi, for a very exciting introduction to your field and excellent overview of your work. So. Any questions? Anyone? So Davide.
Yeah, thank you. Really nice overview and great, experiments and the results. It's really amazing. So the first question that I have, I think I have many, but the first question is there any dynamics in the end in all these? Well, I understand that there is a dynamics of the condensate because you're not exciting the mode 0, but you're exciting some kind of finite mode. So there is some intrinsic dynamics of the condensate, but is there any dynamics on the top of the condensate? Like in cold atomic gases where you can create excitations and see some dynamics on the condensate. Do you see what I mean?
Yes, so this is something that we have not been investigating, but there's another group at the National University in Australia, or the Australian National University, the group of Elena Ostrovskaya, and they have been doing these experiments where they have been looking at the excitations on top of Polaritan fluid, so the Bogoliubov elementary excitations, and they have now, I think, in the past 3 years, I think they published 3 very nice papers about this kind of physics, but I don't know it well enough to comment more on that.
Okay, thank you. So also the vortices that you've shown are completely frozen, like in the center of
yes,
the region, right?
Exactly. So the vortices that I was showing, because this is a system that is driven out of equilibrium, we're really just so the dynamics. You can basically think of the dynamics as just trying to find stationary modes of your system. Of course, we do also have access to non-stationary modes, but in this case here, this vortex example, this is a stationary monochromatic condensate. So everything is frozen, like you said, the vortex is not moving around. Everything is completely stationary and robust. So it's like if I were to think about lasers, it's like kind of a funky laser mode that is very robust.
Yeah. Okay. Thank you. Well, I think I might have some other questions later, but I'll give the opportunity to others to ask. Thanks.
I have a quick follow-up questions to this slide. So you mentioned that by changing the lattice constant, you can change a condensate from evanescent to ballistic. So yes. in this case, can you do it? What happens to the vortices in this case?
So in this case, so what happens if I basically contract the polygon more and more and more? What will happen eventually is that you basically start losing the condensate on top of your pump spots, and the condensate moves towards the center of the system. So you create like a kind of a messy but still a trap which contains the condensate in the center here. And so this is called optical trapping in polaritons. Well, I guess optical trapping applies to also atomic condensates, but this is what would happen if you contract the polygon. You lose most of your emission from top of the pump spots, and your emission starts just going in the center of the system where it occupies some low momentum components.
All right, so you don't have vortices in this case.
Yeah, so you lose your vorticity because you basically go out of this limit where you talk about ferromagnetic and anti-ferromagnetic couplings, because you no longer have well-defined vertices in your polygon. If you contract it so much, it just becomes like a blob. So you no longer have this geometric frustration.
All right, yeah, I see. Thanks. So, Samuli.
Yes, thanks for a very interesting talk.
Thank you.
There were many things that I was going to ask, but one of them is, so I understand, or if I understand, so far everything has been optical, but I mean, for the control and observation of the condensate. Can you think of some combined or completely different way of accessing it, for example, optomechanically or something like that?
Your question is about doing some optomechanics with polaritons.
Well, so, for example, or is there some, I don't know, electric sort of connection that one could imagine making to a condensate of this sort?
So I'm not quite sure what would be the optomechanical response of these condensates, but since you mentioned electric fields, you can control properties of the polaritons with electric fields, because when you apply an electric field to your structure, you change the properties of the excitons, and when the excitons change, you change the polaritons. And it can basically, you can change the dipole oscillator strength of your excitons, which changes the Rabi splitting of your sample, which can affect everything. So you can play around with the properties of the sample by applying electric fields or magnetic fields, but optomechanics, I don't know enough about that to properly answer that question, so I'm sorry about that.
That's fine. I'm just curious.
Okay. Yeah, David.
Well, if I can ask another question, so it's a completely different thing. So, so when you explain how you can realize these Bose-Einstein condensates, so if I got it right, you're basically increasing the density of the photon by increasing the pumping of the laser, right? But how do you control the temperature? So instead of controlling the chemical potential, how or the density, how would you control the temperature?
So experimentally, what do we do?
Yeah.
So so we use a cold finger cryostat, and there is liquid helium that cools the sample down to about 6 or 5 Kelvin. So you need these temperatures just to stabilize the excitons, because if you go to higher temperatures, then your excitons are completely unstable. They will disassociate immediately. So you can use white bandgap materials like gallium nitride or zinc oxide, or some organic semiconductors that have Frankel excitons. They have binding energies in the hundreds of MeV and can operate at room temperature. But we need cryogenic temperatures because this is a gallium arsenide type of sample.
So basically, well, if I got it right, so the temperature of the setup is actually the same temperature also of the boson cloud. So they're in equilibrium.
Well, we don't change the temperature, if that's the question. The temperature is
Yeah,
the same.
no, but somehow you assume that the temperature of the boson cloud is exactly the same temperature of the setup.
Yeah, that is a correct assumption.
Okay, right.
But it's kind of difficult to talk about temperature of this boson cloud because this is an out of equilibrium system. Like you cannot really associate a free energy or anything like that to this system. So
I agree with you, but somehow, I mean, what you say is that you reach condensation. So somehow, I mean, you assume that you are in, well, not saying thermal equilibrium, but like a statistically steady, not out of equilibrium state. And so somehow, I mean, you can extend, I think, the definition of temperature there somehow. I mean, by looking at the fluctuations, for example.
I think this is exactly being investigated even today, but this has been an argument in many conferences. And this is why me, for example, I don't like calling these Polaritan Bose-Einstein condensates.
Right.
I prefer to call them just Polaritan Condensates, because this is just a macroscopic wave function where you achieved a system where basically you achieved quantum degeneracy with these polaritons. Yeah, and there are of course some boson statistics to the to this system, but then there are also some Fermi statistics because the excitons are composite particles. They're made out of holes and electrons. So at high densities, you start losing the bosonic picture, and it becomes even more complicated.
Okay, thank you. Very interesting. Thank you.
Thank you.
Well, yeah, thanks a lot, everyone. We've run out of time now. So I have a couple of announcements. So firstly, this was the last webinar before the break. And well, secondly, if you have new PhD students, new researchers in your group, please tell them that this webinar exists, and it's really exciting. Yeah, so well, thanks a lot, Helgi, again. So it was really exciting talk.
Thank you very much, Timo.
Yeah, and well, see you everyone sometime in September/October. See you.
All right. Thanks a lot. Bye.
Bye. Have a really nice summer.